Okay, so again, this is for those of you that are looking to get to that extension level, especially anybody has pre-calculus. Make sure that you are sticking with through this discussion. Now, for our first example for the setup, we're going to be looking at a problem from your text, 7-31. It's in section 7.1.3. So if you can't read anything on my screen, just pull up your textbook and follow along, please. So, hey, pregnancy. So what we know is, based on this, human chorionic gonadotropin is a hormone that grows exponentially at the start of pregnancy, meaning it follows either an exponential growth curve or an exponential decay curve. When we talk about growing exponentially, that's going to be the growth kind. So it follows that pattern, meaning it's going to fit an equation that looks like this. So y equals ab to the power of x, where a and b are constants. They're numbers that we need to figure out based on the information that we have. So here's the sitch, short for situation. Brad's mother was tested on March 21st. She was at 200 units, and 2 days later, it was up to 392. Okay, believe it or not, that's enough information to figure out what the A and the B need to be. Here's your general math rule. You need to have as many ordered pairs as you have unknowns. So I don't know A, I don't know B. That's two things. So I need two ordered pairs. Well, we've got on March 21st, and then we've got 2 days later on March 23rd. That's going to be two ordered pairs to work with. That's enough. So the first thing to do is make sure we know what we're talking about. So let's define some variables a little bit. In our ordered pairs, we got an x and a y here. Let's just say what they mean. Let x equal. Now, you got choices. I'm just going to tell you what the easiest is. Since this is the first day we have information about, let's let x be the number of days since then. Okay? So that means that I don't have to use like 21 and 23. I can just use 0 and 2 as my x's. It's going to make our life a lot easier. We are going to let y equal the HCG levels. That means then that my two ordered pairs are as follows. On March 21st, so day 0, when we started, we were at a level of 200. And then 2 days later, we were at a level of 392. Now, how do we use these to actually find out what the A and the B should be? Here's the fantastic news. If one of your ordered pairs starts with 0, this process is really pretty simple. It goes like this. Take that equation, put in the numbers. So 200 equals A times B to the power of 0. And then don't overthink it. How much is B to the power of 0? 1 every single time. And 1 times A is just A. So there you go. You have your value of A already. That means that we know our equation looks something like y equals 200 times b to the power of x. We just need to figure out what b is. That's what this second ordered pair is for. So coming over here, just for space reasons, put in your new y. We know that a is 200. We don't know what b is yet, but we know that x is 2. And then we need to get this b by itself. So let's do a division by 200 first. 392 divided by 200 is 1.96. That's equal to b to the second. Let's do a square root. 1.96 square rooted comes out pretty nicely. It's almost like those people that wrote your textbook designed it that way. And there's your value of b. So our equation is y equals 200 times 1.4 to the power of x. Now here's the thing. If you don't have an ordered pair that starts with 0, it gets a little more complicated. After this example, we'll look at a couple others where that's the case. So we've got our model. That's the hard part. Now let's use it. So it does say here that most women generally have an HCG level of 5. So if you're not pregnant, that's where it is. So here's the thing. We're going to work backwards. We're going to figure out on what day her level was at 5. Since that's when she would have started growing, that's when the pregnancy would have first taken root, the embryo becoming implanted. So here we go. Let's take that HCG level, which is a Y. Let's get a pen here. How about? The older version of this program had separate buttons for pen and highlighter. I forget that sometimes. Okay, put 5 in for the Y. Set that equal to our equation. Now we're simply going to solve for the X. So a division, 5 divided by 200. Whoop. I hit the wrong button. There we go, 0.25. Or 0.025 rather. And then switch it over to log form. So because the variable's in the exponent, I need to use a logarithm. So log base 1.4 of 0.025. So as you are doing your calculation, I'm going to do mine. Log base comes out to be about negative 10.963. All right, so about negative 11. Now, let's think about what this means. Remember what our X represents. X is the days since the 21st of March. Okay, well, if I've got negative 11, that means 11 days before the 21st of March. So when did the embryo likely become implanted? Probably about March 10th. How many days after implantation was the first doctor visit? Well, that's what we found here. It was about 11 days. Right, and all right. Now the next follow-up. Brad learned that a baby's born about 36 weeks after implantation. That is actually how they figure due dates. When can we expect the sibling to be born? Well, I'm going to recommend that you just do this. I'm going to go to Google and type in 38 weeks after March 10th. 38 weeks after March 10th. All right, so December 1st is about when we should expect that that new baby to come. So around December 1st. Now, of course, not all pregnancies are exactly the same length, but that's probably not a bad bet if you're trying to plan for when you expect to see the new baby come. There you go. Now, on this next one, no context here. I just made up some numbers. We're going to find exponential models that match these points. And you'll notice, in this case, we don't have an x value being 0. So we're going to fit this equation to these points. It's just one little bit more complicated. Here's how it works. Take this model, and I want you to put both ordered pairs in. So, for example, 2.62 equals, because that's the y, a, b to the power of 6, since that's the x. Then let's do the same thing with the other one. 6.4 equals a, b to the power of 2. Now what we're going to do is eliminate one of these variables. Now you may have done this with systems of equations in a previous class. We're going to do a similar thing here, except instead of subtracting the equations, we're going to divide the equations. And let's see what happens. Here's why we do this. So 2.62 divided by 6.4. All right, don't round it all. I'm going to include all the decimal places. So 0.409375. Here's where the magic happens. Look what happens on the other side here. A divided by A, that's just 1. No more A's. Isn't that awesome? And then as far as the B goes, B to the 6th divided by B to the 2nd. You know from your log properties that you just subtract those exponents, you get B to the 4th. Now to solve this equation, let's do a 4th root on the left and right hand sides. So 4th root of that big decimal number ends up being about, okay, so it's 0.79989. That rounds to approximately 0.80. Now, where should you round to? it depends on your context. For what we're doing right now, 2 decimal places is going to be plenty. Once you've got your b, you're now going to go back to either of these 2 equations, doesn't matter which one, and work backward to solve for the a. So I'm just going to pick this one on the bottom because that's the one that's here. 6.4 equals the a that I don't know times my b to the second power. So 0.8 to the second power is 0.64. Ooh. A times 6.4. Or sorry, 0.64. I put the decimal in the wrong spot. 0.64. So then do a division, you're going to end up with a equals 10. Put that all together, and we've got y equals 10 times 0.80 to the x power. There's your model. So here was our process. This is the recap. Use both ordered pairs to make 2 equations, and then divide them. My advice, have the higher exponent on top. That way you've always got a positive exponent after you do that division. Then work it backward, right? So you eliminate your a, solve for b, and then use that b to substitute and solve for the other unknown. I would like you to try this second one here. Let's see what we get. So like I said, I hope that you are trying yours or have tried yours already as I get mine set up. So 1.90 equals ab to the 8th. 1.64 equals ab to the 3rd. And then divide to eliminate the a's. So 1.90 divided by 1.64. Okay, that does not come out nicely. So here's what I'm going to actually do. I use my calculator to turn it into a fraction because the fraction is unrounded, meaning I don't have to include all the decimals, but I'm not losing any accuracy. So I'm going to write this as 95 divided by 82, right? A's reduce, 8 minus 3 is 5. So my b then is the 5th root of 95 over 82. Let's see if this comes out even close to being nice. Not really. 1.0, now 298689. So no matter where you choose to round, it's going to be right around 1.03. Sticking kind of with our 2 decimal guideline. Okay, so if b is about 1.03, let's then use one of these equations. I'm just going to pick this one since that's what's right there. 1.64 equals the a that I still don't know times b to the 3rd power. 1.03 to the 3rd power is 1.64 equals a times 1.092727. So to finish, just do a division. 1.64 divided by that number turns out to be about 1.5. So a is about 1.5. Put it all together. 1.5 times 1.03 to the x. There you go. You got your model. Process was the same. Use both ordered pairs to write 2 equations. Divide the equations to eliminate the a so you can solve for b. Once that's done, choose either equation. It doesn't matter which one. Put in the number you have for b, work backwards so you can solve for the a, and you've got your model. Now, just an excellent way to check. Let's graph this. 1.5, so 2 my Desmos, times 1.03 to the power of x. And then we had 2 ordered pairs. What were they? We're just going to see whether or not they're on that graph. So 3, 1.64, and 8, 1.9. 3, 1.64. That's pretty much on the line. And then 8, 1.9. That also pretty much on the line. That lets us know that we have done a good job.